Hello. This lecture, slightly different style with the blackboard, is going to be a derivation of the advection-dispersion equation. And this is the standard equation that's used in subsurface hydrology to describe the flow of a contaminant that's dissolved in water. And we're going to derive the equation in one dimension, and then we're going to say something about the solutions. And we're going to do this by describing three physical effects. Advection, which is essentially where you go with the flow, okay? And what that means is that the flux of a contaminant with a concentration C is simply proportional to the Darcy flux, the volume per unit area per unit time. So I'm going to define, as we start, a concentration of pollutant or something that's dissolved in the water. This will have the units, and I'm doing this for my own convenience or the convenience of this equation. It will have the units of the mass of contaminant per unit water volume. Okay. So C is the concentration mass per unit volume here. Okay. And advection, what advection will say is that you have a Darcy velocity, which is a volume per unit area per unit time, the mass flowing per unit area per unit time. The advective flux will be the Darcy velocity times C. Okay? So that's the first physical effect that we're going to consider. The second one is we're going to consider dispersion. Now, dispersion is where the contaminant essentially has a random motion caused by two physical effects. One is random heterogeneity, so differences in the local flow speed that are engendered because there are differences in the local permeability and porosity. And the other is a genuine random motion from diffusion, so diffusive mixing because of the random motion of the molecules. And how we describe that mathematically, and this is somewhat empirical, it's correct for diffusion, it's empirical for dispersion, is using a Fick's-like law, which says that you have a flux, okay, that is proportional to a concentration gradient. So that the flux is a d dc by dx. Okay? And this can be a partial derivative here because the concentration can also vary with time. And the d here is your dispersion coefficient. And the units of d are a length squared per unit time, meters squared per second. And the reason for that is that the flux is a mass per unit area per unit time. This is a mass per volume. This is now a mass per volume times distance. So to make it an area, you need a square meter there, and you need to divide by time. Okay, so the units are right, and this is your dispersion coefficient. The third physical effect is sorption. And they use the word sorption, it could be adsorption, where something just sticks to the solid, or absorption, where it actually goes into the solid. We don't care when we're looking at flow in porous media. The porous media has an enormous surface area onto which components that are dissolved in the water can essentially stick. Okay? And we're going to use a linear isotherm for absorption. So we're going to say that the mass of contaminant that is sorbed per unit rock volume, not per unit water volume, per unit rock volume, is proportional to the concentration. And there's some constant S for sorption times the concentration. And this will be a mass per unit volume, but per unit rock volume. And this is an equilibrium process. Okay, so those are the bits of physics. Now what we want to do is we want to go through the mathematics. And I'm going to derive this equation in one dimension. And the way in which I'm going to do it is I'm going to consider flow in one dimension. Okay, this is going to be the x direction here. And I'm going to take some arbitrary location x and another arbitrary location x plus delta x. And I'm going to consider a box. Okay, this is my three-dimensional diagram. I'm going to consider a box here, and this box has some cross-sectional area A. Okay, and it has some width here, delta x. We're in a porous medium, so we have a porosity, and that's given by the Greek symbol phi. Okay, and now we're going to have some flow. Okay, so let's look at the flow. So we're going to have a Darcy velocity q, okay, and that's going to flow in at the inlet, which is at the location x, so that's what's coming in, okay, and then we're going to have some flow coming out at a location x plus delta x. Now in one-dimensional flow, the Darcy velocity is constant, okay, it's only a function of time, it's not a function of distance, but the concentration may be different here at location x than it is at location delta x plus delta x. So we're going to simply induce conservation of mass. And so what does conservation mass mean? It means the mass that flows in minus the mass that flows out is equal to the change in mass. Simple as that. Mass in minus mass out is the change in mass. So let's do this, okay? And we'll do it using the physical effects that we have here, okay? So I'm going to erase, to begin with this. I hope we can remember these three expressions that we're going to use here, okay? And we also, there's a little bit of subtlety, we're going to consider the sign of this term as well. This is the magnitude. There will be a minus sign because the dispersion goes from high to low concentration. So these don't necessarily add, it's this minus this one, okay? But we'll get to that later. So, okay, we have a concentration C that we can keep. Okay, so now what we want to do is we want to look at the mass in minus the mass out and the change in mass. And the easiest way of doing this is to do the change in mass first, okay? What's the mass in the box at a time t, and what is the mass in the box at a time t plus delta t, right? As simple as this. So at time t, okay, the mass in the box, okay, what is the mass? Well, we've got a volume of the box, okay, delta x times a, that's the volume. So let's put that in, okay, is delta x times the area, okay? That's a volume, but it's a porous medium. So there's a porosity phi, that's the pore volume, and of course there's a concentration, which is a mass per unit water volume. So the water volume is A delta x phi, C is the mass per unit volume, so there's clearly going to be a phi times C, and that's at time t. But just a moment, what about what's sorbed? What sorbed was per unit rock volume, which is A delta x, there's an amount sorbed that's AS times C. That's just the definition. That's the isotherm. Okay, that's the physics. So there is, in fact, an additional term. Okay, an additional term due to sorption, which is ASC at time t. Okay. Now, before we go any further with this, okay, just we have to be aware, okay, of adding these two terms. Okay, now why are we adding these two terms? Okay, this is what's dissolved in water. This is what's sorbed, and we need to consider both. Now, the reason why that sometimes causes some confusion with people is we're going to consider a process here where we have something dissolved in the water, but it also sticks to the rock. It's also sorbed. And what most people think is that's taking material out of the water. And so you have to have a minus sign somewhere to sort of take it out. Where is it in the equation? And so there's this desperate attempt often when you're deriving this to sort of put a minus somewhere. But actually don't do that. That will come possibly from the solution of the equation. it's not actually in the setup, right? If there's a concentration C, it's dissolved in water and it can be absorbed, okay? Just add the two. Just keep calm. Just think about what's in the box, okay? Okay, at a time t plus delta t, the mass is exactly the same. It's delta xa by c plus delta t plus asc t plus delta t. Okay, so the change in mass is actually going to be this one minus this one. So this is the minus sign, this minus that. That's the change. So the change in mass that's equal to A delta X. Okay, and then you notice here we got a phi plus AS, C of t plus delta t minus C t. Okay, that's the change. Now we need to do the mass in minus the mass out. Okay, what's the mass in? What flows in? Well, just a moment, we've got a Darcy velocity Q, haven't we? So mass in is Q. That's a volume per unit area, per unit time. Okay. Now we're going to multiply it by C, okay, because this is now dissolved in water. That's going to be a mass, okay, per unit area, and it's a mass per unit volume. So we need to multiply that by the area. So if we multiply Q by area, okay, and then by delta T, QA delta T is the total volume of fluid that flows, the total volume of water. C is a mass per unit volume, so this gives you the mass in. So that's the mass due to advection. But what about due to dispersion? The dispersion we've just shown has a magnitude d dc dx. Okay, that's a mass per unit area per unit time. So I must multiply it by L delta t, and now that's a mass. Okay, and there is a minus sign here. Okay, the magnitude is dc dx, but dispersion, diffusion, moves things from high pressure to low, high concentration to low concentration. So there's a positive contribution if dc dx actually has a negative magnitude because you're going down in concentration. Okay? So that's why there's the minus sign here. Otherwise you get again, an anti-diffusive process. Doesn't make any sense. So that's the mass in. Now, where is that evaluated? This is all evaluated at a location X. Okay, so this is C at location X where you go in. The mass out is going to be the same expression. So what's out is the same expression evaluated at location X plus delta X. Okay? So it's just the same expression, right? The same mathematics, but it located at here at the outlet, X plus delta X. Okay. So what I'm going to do is now invoke this mass in minus mass out is the change in mass. Okay? And it's getting a little bit messy here. So here we have the change in mass, don't we? Okay, so that's okay. And then what I want to do is I want to simplify this mass in minus mass out here and then make it equal to each other. So this is the change in mass. Okay? Change in mass here, that's fine. And I want to write the mass in minus the mass out. Okay, so Q we know is a constant. D we're going to assume stays the same, and we've got an A delta T. Okay, so all of these terms is going to be A delta T, okay, A delta T, and then we've got the mass in is C at location X minus C at location X plus delta X, okay, and that's all multiplied by Q. Okay. Then we have a minus d, and we have dc by dx x minus dc by dx at x plus delta x. Okay, and that's equal to that. That's equal to the mass in minus the mass out. Okay, so I can actually get rid of this because we have it twice. Too confused. Okay. Right, so now let's have a look at this. Right, how are we going to deal with this equation? The cross-sectional areas are dummy, so that always disappears. Okay, so we never have to worry about that. What I'm going to do is now I'm going to invoke calculus. Obviously, I'm going to have the limit that delta t and delta x go to 0. Hopefully, you can see where that's going to head. Right, partial differential equation. Right, things going to go to 0. So, how do I deal with that? So what I do is I take this delta t and I'm going to put it down here. Okay, so that's delta t here. So that's going to go. Okay. The delta x here, I'm going to divide these two. So we're going to have a delta x here, it's a bit messy, and a delta x here. So that goes. And then I'm going to take the limit delta x and delta t to 0. Okay, fantastic. So what do we get? So this looks, however, the wrong way around, right? Because you used to c of x plus delta x minus c of x. Well, let's put a minus sign to keep it simple. So why don't we put a minus sign out here? And that becomes minus, that becomes plus. This again, minus, plus. Okay. So now what we have is c of x plus delta x minus c of x divided by delta x in the limit that x goes to 0. What's that? Remember your first ever calculus class? dy dx, right? This is dc dx. Okay, let's look at this one. C of t plus delta t minus c of t divided by delta t. That's dc dt. Yeah. This one, I wouldn't say it's complicated, but you know, maybe you have to think a bit, right? dc dx at x plus delta x minus dc dx at x divided by delta x. So it's the derivative of dc dx. So it's d2c dx squared. Okay. So let's get rid of the box now. We actually we've done everything in this box that we can. Okay. So we don't need to worry about it anymore. Okay. We've invoked our conservation of mass. Okay. And we've now invoked calculus. So we got everything here. So let's do it. What we normally do is we normally write this term first. Okay. So we write this as phi plus as, right, dc dt. And you notice here that we have a partial derivative because c is also a function of distance, right? Then what we do is we've got this term that we has a minus sign here, so we're going to put it on the other side, and this is dc dx, so it's plus q dc dx. Okay. Then here we put an overall minus, but there's a minus sign here, so it's actually an opposite sign to this. This is the point we've made before. So we can keep this over this side of the equation because there's two minuses and a plus. So this is equal to d d2c by dx squared. Now, we normally write this equation not exactly like this. Instead of this term, we write this as phi r, where r is the retardation factor. Okay. R is the retardation factor, and obviously by definition, it's equal to 1 plus as over pi. So the form of the advection-dispersion equation that you will see, page 1 of the textbook, okay, it's as follows. And while I'm writing it, I'm going to say why I've spent a little bit of time on the derivation. Is normally when people look at derivations, it is page 1 of the textbook. Okay, boring, now we use the equation. The reason why I'm spending a little bit of time on this is it is important you understand where the derivation came from. It was just counting what's in the box, what goes in, what comes out. It's like, evaluating your bank account. Okay, here's your income, here's your expenditure, that's in minus out. That's got to be in a month. That's what you had now minus what you had in the beginning. Okay, so most people can keep track of money, and they can keep track of money in different places. I've earned some money here. Yeah, my granny gave me some money. I got a tip here, and where your expenditure is in lots of different things. When it comes to flow and course media, funnily enough, if you have more than 2 things to think about, people get themselves in a terrible muddle. No, right? Just keep calm. You need to think what's in the box. Where the stuff is and how it's moving. Okay, and the other thing here with sorption and the taking things away is sorption didn't contribute to the flux at all, because sorption, by its very nature, is the stuff stuck to the rock. So there was no flux term for sorption, okay, because it's not moving. All right, so the sorption only is in the mass, and then the dispersion is only in the flux. Okay, so the form in which you would normally see the advection-dispersion equation written in one dimension, is phi of c dt plus q c dx equals d d2 c by dx squared. And sometimes there is a little subtlety here. This is how I've defined the dispersion coefficient, so that the flux is here. Sometimes instead people put in empirically a porosity term. So instead of writing a d, you write phi d. And there isn't any physical reason why that's right or wrong. It's just a convention. It's then your d is defined differently. Okay? So I've just kept it in the simple form. Sometimes you do see a porosity term there, and that's perfectly legitimate. And there's some good theoretical reasons when you think about molecular diffusion and the nature of the dispersion, why it makes sense to put a porosity term here. But I've just kept it as simple as possible. Okay. All right. That's the equation. Okay, either with a d or a phi d, but this is the advection-dispersion equation. It's got advection in it. This is the advective term. It's got retardation due to sorption, and it's got dispersion in it. And this is called, in letters, the ADE, advection-dispersion equation. Okay. Now what we're going to do is we're going to think about what does it mean? How would you solve it? I'm not actually going to try and solve it analytically. You can solve it analytically with both the advective and the dispersive term. But I'm going to keep things simple in today's treatment. I'm actually going to assume that this term is small. And certainly for homogeneous systems, largely homogeneous systems where the mixing is largely dominated by molecular diffusion, that's a small effect. You normally have a mixing zone with diffusion that's sort of tens of centimeters, as opposed to advection that may extend over tens or hundreds of meters. And so when we're looking at solutions of the advection-dispersion equation, this dispersive or diffusive term can be small. So I'm going to actually neglect it in the equations, okay? And then I will talk about where it comes from, what effect it might have later. So I'm going to put a big fat 0 there. And now I'm going to solve the equation. And when we're looking at this equation, we're talking about something flowing, aren't we? Something moving. So actually, I'm going to look for a solution that's a function just of velocity. I just want to find what's the speed. Okay. Now to do that, then actually, first sight, just looks like a transformation of variables. Instead of having x and t as independent variables, I'm looking for one variable that's x over 2. Okay, it looks a bit strange, but let's see where we head with the mathematics. So if we do this, we just got c as a function of v. I just want to know the velocity with which a concentration moves. Okay. So we've got a dc dt term is dc dv dv dt. Right. Well, often when I explain this, people get really confused because they haven't really got their brains around this transformation. But Could you differentiate this with respect to t at a constant x? It's not difficult, right? It's just where's it heading, right? It's the confusing bit, but the actual maths is easy. Okay, so dv dt is just minus x over t squared, which can be written as minus b over t. Then we got a dc dx term. Is dc dv dx, right? And that's even easier. That's just 1 over t. Okay. So we can just plot this in the equation. Okay, let's do it. Okay, so we get phi r dc dv minus v over t, okay, plus q dc dv, and that's 1 over t equals it. Okay, and well, t's go. Okay, so that's nice. And so let's rearrange that because it's looking a bit strange, but dc dv. Okay, and then we got a minus v phi r. We can rearrange this, right, in a way that makes a bit more sense. Like that. Okay, so that's the solution. Okay, so now we got to the answer. What's going on here? So we've got these two things have to multiply together, have to equal 0. So either one or both are 0. Okay, so one solution is dc dv is 0. And don't dismiss that. What that means is c is a constant. So if I've got some water and there's something dissolved in the water and it's flowing and the concentration is the same everywhere, it doesn't change. And yeah, actually that's fine, right? Right, so we have constant concentration everywhere and it flows, and that's the solution. I know it's a quite trivial solution, but it is a solution, okay? Don't just throw it away, right? It's there. Okay, but the other one that obviously is a bit more interesting is that it says if we have the concentration moving with a velocity, the velocity it has is q over phi r. And that explains why I talked about this retardation coefficient. I just mentioned it, gave it an r, and didn't say anything. R. Well, if there's no sorption at all, okay, r is 1. Okay, if we go back to the definition of r was 1 plus as over phi. So you can't see that. Okay, 1 plus as over phi. So if there's no sorption, r is 1. Right, there's nothing sorbed. And so the velocity with which you move is q over phi. Now, you didn't need a partial differential equation to see that, right? If you think about a piece of rock, right, let's take this chalk, okay? It's got a porosity of about 50%. So imagine I was injecting a cubic centimetre of water every second, and this cross-sectional area is centimetre squared. So every second, how far would the water move? 1 centimetre? No, because it's a Darcy flow, as Q is a volume per unit area, can only fill the pore space. It doesn't fill the solids, does it? So the porosity is 50%. It actually has to go 2 centimetres to get a cubic centimetre of pore space. Okay, imagine the porosity was 25%, a quarter. I'd actually have to move 4 centimetres. Okay, so the velocity, the true average speed with which a water molecule moves, or something dissolved in the water going with the flow, is the Darcy velocity divided by the porosity. You've got this additional r term, which is greater than 1. It's a retardation. It's the amount by which sorption slows down the flow because of sorption. Now at this point, say, huh? Slows down the flow? Doesn't sorption take stuff out? It's in the water and then it sticks and takes it out of the water. Where's the, again, is that minus sign? Actually, no. Sorption doesn't do that. It slows you down. It slows down the flow. And the reason is because it's an equilibrium process. So you've got some initial concentration in your porous medium. That initial concentration is already sorbed. Nothing's been taken out. It's already in equilibrium. Okay, so there's sorbed material and there's material in the water. Now let's think about why does then the plume, right, the amount of the contaminant, why does that go slower? Why is it slowing down? Well, the way of thinking about it is here. Imagine I am a molecule in water, and imagine I'm called what's known as a conservative tracer, which means actually I go with the flow, I don't sorb. Okay, so here I am, a molecule, and I'm going with the flow, and I don't sorb. So right, I just keep going. That's my native speed, Q over 5. Okay, fine. Now imagine I'm a sorbing tracer, right? Something that sorbs. Okay. But remember, it's an equilibrium process sorption. So I start off in the water, as an example. Okay, here I go. I'm in the water. Equilibrium, there's a sorbed molecule, desorbs, I stick. I'm stuck. Don't move, okay? I can't get in the flow. But because it's equilibrium, I'm not stuck here forever. I then get back in the flow. Then I'm moving. Right, then I stick. Then I start moving. Then I stick. And of course, this is a molecular process. It happens millions and millions and millions of times. On average, what it's doing is slowing you down, right? It's the equivalent of sort of playing a game on the underground of the metro where you wait on the platform, train comes along, toss a coin. Heads, you get on the train. Tails, you wait on the platform. If you're on the train, you get to the next station. Heads, you stay on the train. Tails, you get off. Right? It's exactly the same. It's an equilibrium. You're on the platform, sorbed, or you're on the train, going with the flow. That game, you'll still get to your destination, but very slowly. So sorption slows you down. So let's finish this with a graph of what actually the correct solutions look like, because it's sort of very unsatisfying for many people. You know. This is your velocity. That's all you've got. What about dispersion? You know, what's going on here? So let's show a picture of what I mean. One-dimensional flow. Here's x. Here's concentration. And imagine to begin with, okay, at what time t equals 0. This is your concentration C of x and t equals 0, which you can call C naught of x. So your initial condition is, you know, you spilt some contaminant, right? It has a concentration in the subsurface. The concentration is what it is. It can be any function. It's got to be single valued, but it can be the world's most complex function. It doesn't matter. It's what you would measure, right? That's your initial condition. Okay. But it's an equilibrium. So there's also stuff sorbed. It's not, oh, it's going to sorb later with some complex equation. No, it's an equilibrium. It's already sorbed mass as well. And the sorbed mass is just AS times C. Okay, we have a Darcy velocity Q, and that again is another boundary condition, right? It's what the flow is. Okay, if we have a conservative tracer at a time t, what you find, and my drawing isn't very good, it's exactly the same profile, right? This is where R equals 1, so it's a conservative tracer. R equals 1. It's simply moved, if you imagine here, it's simply moved, displaced a distance, Vt, where V is Qt of Q over 5. So that's your conservative tracer. Now, it doesn't look exactly the same. My drawing, as I said, isn't excellent. It goes with the same profile. A sorbing tracer moves slower, so it's the same profile, right? But it's simply moved slower for the reasons we've said. Okay, so here, this is Vt, which is Q over 5 R times T. It's less by R, okay? And it's just conservation of mass, because in this case, everything is going with the flow. Everything is on the train, okay? And so it's all moving fast. Here, stuff is also waiting on the platform all the time, getting in, getting off, getting in, getting off. So you've got the same conservation of mass, but it's moving slow. Okay, the last thing is, what about dispersion? What about that term that we conveniently decided to forget about? What dispersion does is it smears things out. Okay, there's a flux from high to low concentration. So what dispersion would do in this equation is that they've got the same mass, but it smears things out. Okay, and over time the smearing gets greater. Okay, so what we would see here, same area under the curve, but a smeared out profile. And roughly speaking, the amount by which you smear out is approximately root dt. It's a diffusive, it's a random process. The amount of smearing proportional to the square root of time, not linearly with time. And so compared to the linear movement due to advection, all right, the dispersive process at very late times tends to be, relatively speaking, smaller. Okay, so that's why we've ignored it in the analytic solution, but it can be included. But what it tends to do is it tends to smear out the profile. Okay, so that was a relatively simple presentation of the advection dispersion equation. I hope that you found that useful. Okay, so thank you very much.